you saying the squirrel is resistant to diabetes?
So at the beginning of the hibernation period, they increase their body mass by over 100%, and they become completely insulin resistant. So it's a naturally reversible model of diabetes, essentially.
That's insane.
Wow. This is StarTalk Special Edition. And since it's Special Edition, you know my two co-hosts, Chuck Nice. Chuck, how you doing, man?
Hey, Neil. I'm doing great, thanks.
And not only Chuck, we've got Gary O'Reilly. All right, Gary, welcome back.
Thank you. Always a pleasure.
Today's topic is like, whoa, how come we didn't do this 10 years ago? We're going to talk about hibernation in space.
Ooh, don't sleep on this subject.
Ooh, came in early.
I want me some hibernation stories here. So, Gary, set the scene here. What did you put together?
We've all seen the sci-fi movies where the crew are in some kind of deep sleep, hurtling through deep space. But how is that going to be achieved? Turns out we actually may have to look to Mother Nature for our answer. Animals can hibernate for months at a time, from little squirrels to big old bears. So if humans want to engage in interplanetary travel, they are most likely going to need to hibernate or enter a state of torpor. But can you get a non-hibernating animal, which is us humans, to hibernate? And for that, we are going to need an expert. Cue our guest, Ryan Sprenger, PhD, Senior Research Physiologist at Fauna Bio, a PhD in zoology with expertise in cardiopulmonary physiology, also expertise in hibernation and extreme physiology, which I think is a vital component of his background and its effects on the cardiovascular system. Fauna Bio have been awarded a NASA grant through their NAIC program, which stands for NASA Innovative Advanced Concepts for a Study in Torpor in Animals for Space Health, or STASH. Plus, the most important thing is, Ryan is a StarTalk fan, which makes him smart as well as cool.
We love it. Ryan, welcome to StarTalk.
Thank you so much for having me. I'm excited to be here.
So, what is torpor?
That's a good question. What is torpor? So we define torpor in the field as a state of metabolic depression and body temperature depression. And so it's sort of this quiescent state where the body's been turned down.
Wait, so depression in a biophysiological sense, not in a neurological sense?
A little bit of a biophysiological sense in its root, but you also have a neurophysiological depression.
But not a depressive state as in an emotional...
That's all I mean.
Yes.
Yeah.
Got it.
So it's a dialing down of the metabolism and the body temperature, essentially. The body pulling
torpor.
back.
So what's the difference between torpor and hibernation?
This is a fun topic to discuss at the hibernation conferences that we hold every 4 years. But what the general field will say is hibernation is the season in which the animals will use torpor. And so torpor is the actual state in which the metabolism is low.
Why do you have conferences only every 4 years? Are you hibernating in between?
Yeah, precisely. Well, that's when good science gets done as well. Well, historically, it's taken longer to collect hibernation data because it's a seasonal event.
Yeah, you only have a very limited window where you can study.
Yeah,
you can't go up to a bear in the summertime just like, hey man, you tired? You need a nap?
Mind you, you've got two hemispheres right, where winter is one time and in one and a different in other. So you might, it depends if you feel like picking up your bags and traveling.
Yeah, well, actually, and that's why it was just this year we decided to shorten that as a community. We decided to shorten that conference because we're learning that hibernation is not just a cold season event. We're learning recently that warm animals will hibernate. Animals in warm climates will hibernate. They'll hibernate at warm temperatures. So we're learning that it's more widespread than we thought.
Why do they do it? I mean, what is the purpose of hibernation for? Like, if I'm a bear, right? We all think of hibernation. We automatically think of bears. So I use them as an example. But why not just be awake all year long and go get some food or pack up on calories like some other animals do, and then get through the lean time? What's the idea of dialing yourself down metabolically and taking a long nap.
You mentioned it almost in your question. It costs a lot to do things is a really simple way of putting it.
Energetically.
Energetically. It costs a lot energetically to do things.
I'm not thinking the bear's needs $20 in his wallet to go to the store.
No.
Very costly to be a bear, man.
Only you can prevent forest fires. Come on, help a brother out.
Spare change. Energetically, it costs a lot. And so even if you wanted to pack on all that extra weight and try to make it through a period of what we like to term resource deprivation. So this is a period where there's not as much water available, it's frozen, or it's a drought. And there's not a lot of food available because of that reason. And so in these periods of resource deprivation, some mammals have decided over time to instead of increasing supply, they decrease demand. And that demand being your metabolism that they're turning down.
Oh my, that scares me in a way, just because I think about the climate and how it's changing. And when you talk about matters of deprivation, or lack of resources, we might find a time where maybe those bears won't hibernate because the water won't be frozen. And then we've encroached upon their land and they're like, hey, you guys are supplying us with food. Like, because you ever see the videos of them tearing open a car to get to that picnic basket? It's a little scary when you describe hibernation that way for those reasons.
Yeah. Well, bears are very strong animals. That goes without saying. But climate change, actually, that's a big push in the field right now, is to try to understand what climate change is going to do to hibernators, particularly the cold climate hibernators, because again, we're seeing more and more warm climate hibernators. So we have an idea of what it might look like, but it is very different. So it's going to be a big change for a lot of these species.
There has to be some positive benefit to hibernation. Otherwise, animals will have evolved not to do it.
Most mammals don't do it.
What are the benefits then apart from getting a good nap?
It would be the dream if you could. The benefit, as far as we can tell, is these animals that use it are more resilient to periods in which there suddenly isn't availability of resources.
Gotcha.
And so a really great example of this actually is not in the northern hemispheres where it's cold. It's the southern hemispheres in Australia where you have big wildfires.
Ooh.
And there's animals down there that after these periods of wildfire where there's now suddenly no food for a while, they'll go into torpor. And so these animals are more resilient now because they don't need that food and they can survive a little bit longer. They can just kind of stretch what resources they currently have in their body. And so
cold-blooded animals barely eat anyway, right? I mean, we always show alligators as being voracious eaters, but we eat a lot because we have to maintain our body temperature apart from the air temperature surrounding us. If they are the air temperature, then their energy is for what? To run their brain, and if they want to just walk around a little bit?
Exactly so, yeah. And so you're exactly right. The cold-blooded animals, they don't eat a lot. They can go quite long periods. Alligators, I think, can go months to almost a year without eating. Yeah.
Oh, my God.
And I've got a funny anecdote about that from my old advisor. But
there's nothing funny about a hungry alligator.
I was about to say that.
No, not at all. Not when you're around it, at least. Yeah.
That's right.
But yeah, they don't eat for long periods of time because they don't have to defend body temperature. So defending body temperature at a stable amount is it costs a lot of energy.
So we're expending energy all the time just to keep our body temperature at 98.6 is what you're saying.
Exactly.
Like that's where so if you don't have that, I'll call it a problem, but if that's not necessary, then you're saving a lot lot of energy.
You barely have to eat at all.
You're running
to
stand still.
You barely have to eat at all.
So,
exactly.
Yeah, in fact, it's worse than that, or better than that. You burn energy thermally just by maintaining your body temperature, but you also burn energy kinetically, right? By like moving against gravity or just moving at all. Okay. Consider how long it would take your body to burn the calories of a cupcake just by existing. You will easily burn the calories of a cupcake just by watching television. You can do that. Okay.
Right.
But then say, what do I have to do on a treadmill to burn the calories of a cupcake? It's like, I'm not doing that.
Right. Yeah. That's damn near an hour running.
Yeah, exactly. Exactly. Yeah. Thermal energy is a huge consumer of energy relative to kinetic energy. But Ryan, get back to your answer there. if there are wildfires and they take out resources, you have to wait until the trees grow back and the bushes grow back. It seems to me that would require a much longer time than a typical hibernating bear for the resources to return if they have to recover from a wildfire.
Yeah, I would describe it more of a strategy to stretch how long you can maintain in that area.
Okay.
And so if you stay active,
Anything helps.
You've got days, right? If you stay torpid, you've got months, and they can stay in torpor. I mean, there's animals that, again, and these are in the northern hemispheres, but there's animals that can stay torpid for 9 months of the year.
Oh,
and so
wow.
It's quite a while. And your primary growth, or your secondary growth, I should say, your primary growth, sorry, your first shrubbery where you can start to get things to eat, like insects and berries if they're coming up in those months. You could stretch yourself to get to those, I would say. Yeah.
Okay, so what does NASA want out of you here? And Fauna Bio, is that a company you started? What is Fauna Bio?
Yeah, Fauna Bio is not a company I started. It was started by 3 really intelligent ladies, Katie, Linda, and Ashley.
By the way, I've never heard anyone say, my company was started by 3 stupid people. Okay, so
that's a good point. That's a good point. I just like to give them credit when it's due. They're really incredible human beings. The company is based on the premise that a lot of drug development could be benefited by looking at animals that have extreme physiology, or rather looking at animals that are good at defending against diseases that humans are afflicted with naturally. And so one of the models that we use quite regularly is a hibernating species called the 13-line ground squirrel. And that species is fantastic against things like diabetes, ischemia reperfusion, for example. So this is after traumatic injury, loss of blood flow, loss of oxygen, you return that, you get tissue damage.
Wait, you're saying the squirrel is resistant to diabetes?
So at the beginning of the hibernation period, or before they start their hibernation season, they increase their body mass by over 100% just adipose tissue. So let's say they weigh 100 grams, they'll go to 250 grams. They've added 150 grams of just fat. And they become completely insulin resistant during that period. And by the time the end of the hibernation season comes around, they reverse that insulin resistance and they're back to normal.
Wow.
So it's a naturally reversible model of diabetes, essentially.
That's insane.
Wow.
Yes.
That's so, I mean, why isn't everybody studying? I mean, diabetes is a huge problem in this country. Huge.
Right. So if we know we mammals are a branch of the tree of life, and so we have more in common with each other than either of us have with any other branch in the tree of life, why can't we just genetically steal these DNA secrets in these animals and then apply it to us for whatever, however we need? And is that what NASA is trying to get you to do for our future astronauts?
Yes. That is what fauna is trying to do using these extreme organisms. And hibernators aren't the only species that are extraordinary. There's a spiny mouse, for example, that has regenerative capabilities. So this is a mammal that can
spiny mouse.
Yes,
Spiny
mouse that has regenerative.
What are the regenerative capabilities? Per se.
We grow a tail or a leg, right?
I don't know about a whole limb, but certainly tissue replacement. So neural tissue replacement, skin, like dermal tissue replacement, so skin.
Is there not a chance for any mammal that hibernates for any length of time losing muscle density?
This is another remarkable aspect of the hibernating species that have been studied to date. They don't. So yeah.
Here
so
we go.
this
Game
is incredible.
changer.
This is
where
NASA is interested.
Yes.
This is where we get into NASA. Yeah. So if you break your arm, your leg, you go into a cast for however many months that you have it on. You take it off. Your arms are different sizes. You've lost muscle mass. That's disuse atrophy is what it's called.
I'm old enough to remember the old days where you were encouraged to not use the limb at all. There were no walking casts. There was no exercises you would do. And I had friends who broke limbs and they took off the cast. It was like the limbs of 2 different people on the same body.
Yeah. Yeah. And hibernators don't do that. It's incredible.
Wow.
Yeah.
But you always see in the nature shows where the animal comes out of hibernation and then, sir, what's his name? I forget. And he's just like, and now the feverish search for food begins. Like, they immediately have.
Attenborough. You
How
call that
dare
Attenborough.
you
Oh,
forget
yes.
Sir
Attenborough,
David
yeah.
Attenborough's name?
That's his name, Sir David Attenborough. Yes, exactly.
That's why he's a
Right.
Brit. We're allowed to forget it.
Yeah. Well, no, he's beloved everywhere.
Oh,
he's
he's-
not even like the whole world owns that guy. That's why I couldn't
Yeah.
remember his name because everybody knows. So you're saying that the weight loss is not muscle density? It's
Correct.
So they put on fat, and then all they do is their body eats the fat.
Yep.
Oh,
yeah,
because
they
our body
change-
eats muscle.
For muscle first.
Yeah, our
you're
body eats
absolutely
the
right.
muscle first.
Ryan, why don't you fix us?
Actually, Fauna just signed a really awesome partnership with Eli Lilly trying to fix that. Yes, we're doing that. We're actively looking at that, actually. We're looking for new obesity targets to try to see how it is that we can have our metabolism say, yeah, we want to just consume adipose. We don't want to consume protein. We don't want to consume carbohydrates.
You want to have your metabolism and eat it too.
Exactly. Yeah, that's
Right.
what we want to do. Yeah.
Ryan, in
Damn.
our research, we came across a nugget of information that is worrying and amazing in the same breath. How did we find out that hibernating animals have a level of protection from radiation?
Yeah, this started in the early 50s. I think 51 was the first study that looked at irradiating hibernators. And so they basically gave them huge doses of gamma radiation. And what they learned was that these hibernating species survived the radiation far better than a rat, for example. And it particularly increased, their protection against the radiation increased if they were in torpor. And so these species are uniquely protected against radiation. The study started in the early 50s. We still have not a great idea of why.
It's not because the fat absorbs the gamma rays, is it?
No, we think it has to do with reactive oxygen species.
Please explain what that is.
Yeah, reactive oxygen species are, well, I guess I'm not a chemist, so I couldn't tell you exactly what a reactive oxygen species is, but it's a product of your metabolism. And so these reactive oxygen species, they, as the term suggests, they react with oxygen and they cause all sorts of bad stuff to happen in your tissue damage essentially. And so when radiation comes in and hits a hydrogen, so like a proton comes in and hits a hydrogen, or interacts with oxygen, it creates these reactive oxygen species that damage your body. And so if you've ever been to the store and everybody, the craze right now is antioxidants, if you've seen that in the store in your food, they're designed to counteract reactive oxygen species source.
I'm not anti anything, by the way.
That's fair. And so that's where we think a lot of the protection is coming from, is because these animals are really good at natural antioxidants. So they have them during the torpid state. But also with the reduction of metabolism, you get a reduction of the mitochondrial function, you get less oxygen in these tissues as well as less water. So there's less things for that radiation to interact with and create these reactive oxygen species.
So less things, you mean there's less active biology to disrupt. Is that a way to say that?
Yeah.
And do the animals come out of hibernation after being radiated with gamma rays going like, bear, smash? Or...
Wouldn't that be neat? No.
The bear doesn't have to become whole.
I do not want anyone
the
to
bear
fire
doesn't-
gamma rays at a bloody bear. Do not want
No,
that going
please.
green and Hulk.
Don't. Yeah. I don't. The chance is small, but it's big enough.
Yeah.
Yeah.
So now when squirrels go and they're not hibernating then. They just fill their lair with nuts and stay in for the winter and eat. Is that the deal? Or are they actually hibernating too?
So the ones that everybody's seen in their life, the tree squirrels, big bushy tails, they don't hibernate. You're right. They're food caching animals. So instead of turning down demand, they store away supply essentially for the
Okay.
winter.
All right.
Yeah.
So I can't sneak
Yeah.
up on them during winter and get them.
No, unfortunately not.
There goes that.
Yeah,
There goes that theory.
The squirrel is different from poking the bear.
Yeah.
That's very true.
So there's no understanding biologically why a hibernating mammal would have more radiative resistance. It's not clear why that would be so evolutionarily. Is that right?
That's a really great point. There really seems to be no reason evolutionarily why they would act. I shouldn't say actively, but why that trait might be selected for. So it's probably a passive consequence of some other thing that they've been defending against with the physiology of hibernation, or torpor, I should say. So sort of accidentally becoming more protected against radiation is how I describe it.
Wow.
All right. So where does this go? You're trying to help NASA, at least for Mars missions, where it's 9 months there and 9 months back, and and 2 years on planet. Are there specific missions they're tasking you to think about?
So right now we're in the conceptual phase of NAIC. There's 3 phases. Conceptual, phase 2 is more, you make the concept come to life, and phase 3 is sort of flight mission. We're in the conceptual design. NASA has turned its attention towards trying to figure out the hazards of space, because with the Mars missions planned coming up, they don't have really a good answer for things like radiation, disuse atrophy, lengthy stay in space, essentially. And so they started to drive down different ways to mitigate this. And one of the ways that they've been really interested in is hibernation. And so our unit, what we're designing with NAIC right now, is actually just the ability for the first time in human history to study hibernation in space, because we don't even know if hibernation will work in space. Nobody's even thought to send a hibernating animal up and say, does it happen?
Are there any primates that hibernate? Because I'm thinking theoretically, if there are, then that might be possible for humans.
They'll be even closer to us in the tree of life.
Right,
Yes.
rather than
Yes.
trying to think about how we rework a bear or a squirrel or whatever it might be.
Yeah.
Or a mouse.
There is
Yeah.
one primate, my son.
Hibernate.
That makes
Yeah.
2 primates then, at least.
Oh, there is. Okay.
There are so fat-tailed lemurs from Madagascar. They will use torpor quite well, actually. So there is a more related species to us that can use hibernation.
Is this during ski season in Madagascar? I mean, when would they?
Drought is the big one for Madagascar.
Drought.
Yeah.
Drought.
Yeah.
Right.
So during the dry
So
periods. Mhm.
what chance is there that we share part of that code that will allow us as humans?
We think actually a pretty good chance. We think so. If you look evolutionarily, it seems that hibernation is a pretty basal condition. And what I mean by basal is it's pretty far down in the tree of life
Deep
that
in
it
the tree of
started
life.
to crop it. Yep.
So you wouldn't have to gene splice it. You would just have to gene enable it.
Unlock it.
That's
yeah.
what we're thinking.
You
Yeah,
just
that's what we're
unlock the
thinking.
gene.
Mhm.
Interesting. So now, how do we know physiologically how they? Because we without water we die very quickly. So what is happening physiologically? Are they storing water? Do their cells just retain it? I mean, what's going on? Do we know?
Yeah, we have an idea. Yeah, they
You got a soda
recycle.
machine in the back.
Yeah.
No one's ever been
Yeah.
deep into a bear cave to deny that story.
Yeah, that's true. Well, actually, I might know somebody who has been.
Used to know someone who did.
Yeah, used to. That's a good point.
I mean, specifically with the Madagascar fat tail, because they're primates, and so like I said, we die very quickly without water. So what's going on with them?
Yeah, that unfortunately we don't know.
Okay.
They're incredibly endangered species, so more invasive studies on them they just don't happen. So what we can do is whole animal physiology or survival physiology, but we can't really tell cellularly what's going on with the water in lemurs. Now we can infer from other hibernating species, and we know that they're really good at recycling the water that they do have. So there's a change in renal function essentially that allows them to recycle a little bit better.
That means they don't eat. They don't pee the whole time.
They don't eat, they don't drink, they don't pee, they don't poop. It's a complete shutdown of metabolism.
Wow.
And everything that comes from it. And
so what bodily system, what brain system is controlling all of this? Because it can't just be and that's it. Something's got to still be going on to control this.
Yeah, there's tissues that are still active. So there are neural tissues that are still active. Generally speaking, the cortex is quite quiescent. So there's not a lot going on in the cortex. The neural tissue that we see going on is coming from either the brain, well, both the brainstem and the hypothalamus. So brainstem's controlling all of heart rate, respiratory rate, things like that, keeping your blood moving, even though it's moving more slowly, and your lungs functioning. Obviously, with that, there's muscles that do stay active, like the diaphragm. Some of the upper respiratory muscles will stay active. The hypothalamus, I don't know if you've read about this tissue before. It's basically one of the main tissues controlling metabolism and body temperature. And so they are regulating really tightly where their metabolism is at and where their body temperature is at with the hypothalamus. So that tissue is remaining active as well. And that's actually in and of itself really interesting because you have tissues that are functioning in a mammal at 4 degrees Celsius, which is something that a human couldn't do right now. We couldn't bring a human down to 4 degrees Celsius and ask those tissues to continue to work. You'd get complete neuronal failure. And so they've developed or evolved these ways to maintain tissue function despite it being really cold.
Man, this sounds like sci-fi. It's so cool. Like That's amazing.
Yeah.
Right, so can we get quantitative here? So
Sure.
my basal metabolism, so just keeping my body temperature for 24 hours, I run through between 2,200 and 2,400 calories.
Not for a man your size.
Well, for me, yeah.
Nah,
Yeah.
come on, man.
What are you saying?
You too big to be living on no 2,000 calories. Get out
I
of
didn't say
here.
2,000. I said 2,400. 22, 20, around there.
Okay, all right.
All
If
right.
you say so. I mean, if that makes you comfortable.
Let me live in my own lie.
When he's watching TV.
Okay. So if I'm in one of these hibernative states, what does my calorie needs drop to?
If you're in the hibernating state. So it depends on
Let's
what...
just use round numbers. Just call
Yeah.
it 2,000. So
Yeah.
now what?
It depends on what depth of hibernation we achieve. So if you're
Total
a bear,
depth.
total, the deepest depth, you would be down in the tenths of a calorie. So it's about a 9 per day. Yes.
Per day.
Yeah.
What?
Yeah.
From
So,
2,000 down to less than 1 calorie per day?
so the deepest hibernators that we've seen, they'll reduce metabolism by about 99%, a little bit more than 99%.
Damn.
Oh.
Yeah.
That's insane.
So how?
Okay, but that's still that way.
I want this so bad. I want this so badly.
And that metabolism that's going, it's only adipose.
Just to be clear, 99% drop on 2,000 calories is 20 calories.
Oh, okay. Yeah, you're right. I'm bad
Yeah.
at math, I suppose.
Okay.
It's not like a fraction
Well,
of a calorie.
but I did say it's more than 99%. It would be in nearing the single digits of calories is what you would expect.
That is crazy.
Yeah.
Okay. So to Chuck's point, how can you induce a state of torpor? Because you can't just say, right, lie down there and don't think about calories. So just things have got to
just
happen.
Put it out of your mind.
Yeah, just forget
Yeah.
about it.
Listen to a meditation tape. You're halfway there.
Right? And
Yeah.
how long do you expect a human to be able to go in a state of torpor? Because, you talk about that squirrel that did 9 months. Is that viable for a human?
Well, to answer your first question, how do we get... So naturally, there's a lot of circadian rhythm that's associated with it.
Oh,
So
okay.
the light cycles
Right.
will kind of tell these animals where they should be. Obviously, there's the facultative side of it, which is basically means as soon as the food is taken away, that tells them, I should go into hibernation. So your pet hamster, if you've ever
Yes.
heard the stories of people walking in on their thought dead hamster, that's a facultative hibernator. So that trigger for them is the food's gone away, I must hibernate now. So they'll go into torpor. And so there's different ways of doing it. We're actually getting really good at, over the last 10 years, we were getting really good at taking animals that shouldn't be in hibernation and putting them into hibernation.
Oh.
And so rats, for example, are a prime example of this. We can go in and we can change things in the hypothalamus to make them drop metabolism and drop body temperature to look like they're in torpor.
You take food away from a human, they get hangry.
Very hangry. Yeah.
So you've got to So you're going to have to possibly chemically induce this.
Yeah, there's probably some chemical induction that will be involved in that process. Yeah.
When you talk about the circadian rhythm of human beings, it's pretty particular. So, you put somebody to sleep for a couple months, there's going to be a huge adjustment period when they come out of that. I mean, you want to talk about being disoriented and now they're up in space on top of that.
It's a lot of stuff to throw at
Seems like
somebody
a
at once.
lot, man.
People get really hangry for less.
That's true. What we learned, though, is that circadian clock in the hibernators, it actually continues to function in torpor, but more slowly because the metabolism is slower. And so the same amount of time has elapsed in the circadian clock, despite it being a month versus a day, for example. And so that might help with that disorientation.
If we bring it back to Earth just temporarily, if a bear comes out of torpor, it has a reboot. What if that reboot doesn't quite work 100%?
Yeah.
I mean, all the organs have to go back to 100%.
When you're in space and a human's going to come out and the reboot doesn't quite...
This is something that the movies don't get right.
Oh, it's the only thing the movies don't get right. Yeah, okay.
Yeah, the only thing, everything. No. The other thing is we can't freeze people. That's gone out the window a few years ago. It's incredibly taxing to come out of hibernation. It's actually the most physiologically demanding part of hibernation, I would argue, because everything has to come online in the correct order. So the heart can't pump too fast before the peripheral tissues are ready. You can't inflate the lung too much because it's still cold, so you could break alveoli. So there's and so there's an incredibly coordinated event of these animals coming out of hibernation. So that process is actually quite slow. In a rodent, it could take as long as an hour or two to come out. In a human, in a bear, it's a little bit less because their body temperature started a little higher, the metabolic rate's a little higher. They don't go as deep into hibernation, but it still takes time and it's dangerous.
At the beginning of Austin Powers, where they brought him out of deep freeze, and they thawed him out, he peed for like 3 minutes.
At no point was that for comedic effect.
I'm just saying we all pee like a lot when you wake up in the morning, and this was obviously an extension of that. So I'm still wondering how you pee. If you're not going to pee when you hibernate, you're gonna have a big ass pee when you wake up out of that. No,
well,
maybe.
And I know from experience, there's not a lot of urine after the hibernation period. Not that I hibernated. I've seen it in these animals, but that bladders.
Chucky slipped up.
That's really going to have an effect on the kidneys and the kidney function.
Yeah, renal function is quite dramatically changed in hibernation. But yeah, the bladders aren't full at the end of the hibernation period. They don't urinate, and so it has a lot to do with the recycling of that water, but also the reduction in metabolism. So you're just not using as much of that water as well. Yeah. In sleep, you're still quite metabolically active in sleep.
For an animal that doesn't naturally hibernate, say a human, coming out of hibernation, a torpor, if it's not programmed naturally to get it right, it could go cataclysmically wrong.
Yeah,
certainly could. Yeah. Yep.
Oh, what a great thought.
Is the closest thing to torpor for a human being going into a coma? And would there be any benefit in sustaining us the same way we sustain people who are put into like a medically induced coma or like?
Yeah, that's a great thought, actually. I would argue the closest state to hibernation that humans achieve is actually sleep. What we're thinking is that hibernation is an extension of sleep. But I will squash the media mistake. Hibernation isn't sleep. Actually, they don't sleep in hibernation. In fact, it seems that they come out of hibernation to sleep, but they're not sleeping when they're in torpor. But everything physiologically speaking in sleep is very similar to hibernation, except it's just far deeper in hibernation. But you're exactly right. I think what human hibernation is going to look like is some sort of assisted state, because we're not natural at it right now, and there's a lot of hurdles that we'll have to overcome to get to the point where we can just induce hibernation in a person and then have them come out by themselves. I think in the meantime, it will have to be some sort of assisted state where we're maintaining fluids or nutrient balance at the right level. A whole host of things, really.
How close are we for this being real?
That's a great question. We don't know. It's certainly not a 5 years sort of thing that we can get humans into hibernation. But maybe are we looking in closer to 10, 15 years? I would say realistically.
Are you the first volunteer?
I would happily. Actually, there's a lab with some NASA funding as well, trying to extend the depth of metabolic depression in humans, or reduction in humans, I should say, from sleep using chemicals. And that's the closest I think we are right now to getting humans into a more metabolically lowered state. So we're already starting to cross that starting line, I would say, to getting humans closer to a metabolically lowered state.
Can we jumpstart that by gene therapy?
Jumpstart the entrance into like a torpid state, you mean?
Yeah. Can we give the upgrades to the areas that we, because I'm on the team now, that are really necessary for these things to be in the right place and go in the right direction?
I think we're going to need to do that. What we don't know yet is exactly where to put those jumper cables.
All right.
Where's the right spot to be making these changes to do it, to go into a torpid state more reliably? We know the hypothalamus is going to be important to this endeavor. We know that changes there are going to be key, but we don't know exactly where in the hypothalamus yet.
Okay.
But there's a lot of problems with it that come with just depressing metabolism and lowering body temperature and things like that. There's a lot of problems that we'll have to solve at the same time.
And what about, because we talked about the cast and the atrophy, so muscle atrophy, even if we just sit around, so, just the fact that we're not exercising, which is what our bodies are kind of made to do, So how do you combat the muscle atrophy associated with being asleep for a couple of months?
Yeah. And that's one of the big problems that we're going to have to face. And that's why studying hibernators, natural hibernators, I think is going to be key to figuring that question out. We don't know, really. What we know is that it's a balance between protein degradation and protein synthesis. That's really where the muscle tissue balance comes from. It's either you increase synthesis to maintain tissue or you decrease degradation. And what we see in the hibernators is they actually do a little bit of both in torpor. So they'll decrease their degradation pathways and they'll increase their synthesis pathways. So they're actually making a little bit of new muscle too in the hibernation season. And so what we have to figure out from them is what is it that they're doing to maintain both of those sort of at a higher level. And the answer to that is just we don't know.
You wouldn't be able to use one of those like electronic muscle stimulators that you see advertised in the back of the magazines. Like, put this on, you'll have 6-pack abs in 3 weeks.
Yeah, forced muscle contraction. It's probably not the way I would go. I think there's a more sophisticated way of doing it, but that's more or less what, like, for example, an astronaut has to do is without the electronic stimulation, they have to basically weight train or resistance train.
Resistance, yeah.
A lot of the time that they're in space is because they have to sort of combat that microgravity that's not giving the muscle cues to stay full of tissue. They'll start to degrade.
All right, this is a question for Neil because you just made me think of it. So I'm sorry that I'm directing attention away. But
okay.
You just said in space they weight train, so the weights don't have any weight or you know what I mean?
Resistance.
Like they're
It's not weight. It's just
yeah.
you can use springs.
Yeah.
Springs.
Yeah.
Okay, like the rubber bands.
Right.
Okay.
All right, let's leapfrog to a positive future, Ryan. Say you are able to induce a state of torpor. We're in our spacecraft. We're going interplanetary. What are the logistics that we will need? Is it a nice cozy bed? Are you going to be slopping around in amniotic fluid? What do we need? We need oxygen. We need to be consideration of the CO2 that we're expelling, hydration, all these other things. What are the logistics that we need to be coming to terms with?
Yeah,
I need a Tempur-Pedic mattress, okay,
well,
Ryan? I'm just letting you know.
Retrofit the pods with a Tempur-Pedic mattress. Yeah, I've liked watching movies in the sense of there's a lot of creativity with what they sort of make these pods look like.
If you're weightless, you won't need a mattress. Just thought I'd
That's got a point. Yeah.
They advertise we are used by NASA.
Yes, they do.
Space, and you only need it for the 8 minutes you're going into
right.
And the rest of the time you're weightless. It doesn't matter if there's a mattress there at all.
That's true, because the depression that is from the takeoff, and that's it.
That's it.
Yeah.
Mm-hmm.
So what are they sleeping in space?
Space.
Space.
No, they have these little sleeping bags that they slide in.
Oh, okay.
Keeps them warm. Yeah.
Okay.
But I interrupted.
Keeps them from floating around. No, it's totally fine.
Yeah, especially keeps you from floating around into somebody else's.
Well, to that same token, I think someone in a torpid-like state in space is going to need some sort of sequestering environment, so like a pod, kind of like what you would see in the movies. And I would say, yeah, CO2 is probably my main concern when it comes to hibernation. Once you have that lowered metabolic rate, O2 becomes less of a concern. Obviously, you still need it, but you don't need as much. But CO2 will still eventually build up. So you're going to have to sequester CO2 away or recycle it into O2. I think that humans are going to need some sort of supportive fluids. And the real question is, what is the hibernation going to look like? Because in natural hibernation, they don't just go into torpor and stay in torpor. They actually go into torpor and they periodically spontaneously come out of torpor for about 24 hours. And nobody has any idea why. And then they go back in and they just repeat that cycle throughout the entire hibernation season.
It's like us waking up in the middle of the night.
Exactly.
What's the timeline on that cycle?
Depending on the species. So on the most robust hibernators, like the 13-line ground squirrel, they'll stay in that torpor period for about 20-ish days. And then they'll arouse spontaneously, go into this what we call interbout arousal. And they'll stay in that between 12 and 24 hours, and then they'll go back into torpor for that about 20 days. And when they come out of hibernation, that's actually when they sleep during the hibernation season. So it seems that they still must sleep like all other mammals.
So the sleeping, which we always heard about as a neurological necessity, what you're saying is whatever's going on in hibernation does not serve the body's needs that we get from sleeping.
Precisely.
Interesting.
Yep. So you still have to come out and sleep.
Maybe the cycle of torpor for humans might be a little different where we're in torpor for 4 days and then we come out for 3 days instead of being in for a month. And, you know, is that
That's what you're going to figure out.
Be.
Our formula might be different.
Yeah.
Our formula, I think our formula will certainly be different. And actually, the bear is a prime example of why our formula will be different. Bears don't have the interval arousals. And so there is some sleep associated with their torpor-like state. And that's why we think it's more of this continuum from sleep to deep torpor, is that bears sort of are on the closer to the sleep side, where they don't need these interval arousals. So they must be sleeping in some fashion in their torpor hibernation season. And so I suspect humans will fall on that side. They'll look more like a bear.
Do you participate in the fat bear photo contest?
I don't, but I'm just hearing of this now, so I think I might have to.
Yeah, every fall, I think it is. People they get, you know, whoever's in the wilderness, they get the fattest bear photo they possibly can.
Yeah.
And there's some fat ass bears.
Oh, they get really big. Yeah.
They get, oh my God.
So
all adipose tissue is what they're putting on too.
It's all what?
All fat tissue. That's what they put. It's all fat.
So
Yeah.
Ryan, at some point, you're going to want to test on a furry creature and send them into space. Tell me it's not going
Last I saw your chest hair, you would count as a furry creature.
Yeah.
Barry.
Yes. However, you're not suggesting you send a big old bear up into space.
No. I mean, in reality, that would be the most informative thing to put into space would be the bear, because I think that's what human hibernation is going to look like. But I don't think that's ever going to happen in the near future.
Can you imagine it wakes up grumpy?
Yeah, imagine. Grumpy bears in space.
You know, for a reality check here, the only difference between a bear in a cave and a bear in space is that a bear in space is weightless unless the spacecraft spins up and creates artificial gravity. If it creates artificial gravity, then the difference between a bear in space and a bear in a cave is zero. There is no difference other than there's no salmon swimming by.
Right.
So what are we actually testing for? Is it just a 0G effect?
Yeah. So 0G and radiation. Those are the two things that you're really not getting on Earth that you will be getting in space. Now, this is outside of low Earth orbit, obviously.
Yeah. There's that radiation again. Just to be clear, when you're in low Earth orbit, you're still shielded by Earth's magnetic field. A lot of the high energy rays.
Wow.
But if you're going to go to anywhere other than low Earth orbit, you have a radiation dose that will matter to you. And of course, if you're more radiatively resistant in hibernation state, then it all works out. So maybe all of the radiatively resistant hibernating animals came from space.
In that line of thinking, that makes sense. Yeah.
The aliens brought them, and the ones that didn't survive the radiative, they died. The ones that did came to Earth. There it is.
Go. That's the newest big thing.
And that's your next Pixar movie. Bunch of space animals here.
I'd watch it just to see.
So Ryan, we got to call it quits there. But this has been a highly illuminating conversation. I'm delighted to learn that we got top people working on this. I've always been jealous of other animals. People say, "Oh, the human body is some perfection." No, it's not. There's plenty of other animals that have features that I would delight in.
Yes.
That we don't. Among them, regenerating limbs.
Yeah.
Hibernation sounds like fun if you just want to chill for a couple of months. All of this.
Yeah.
So I'm glad to know we got good people such as yourself and your three leaders tackling these kinds of biomedical challenges and applying them to NASA. This is all great to learn here.
Thank you so much for having me. It's been a really great time talking to all of you. And hopefully it was a fun conversation for everybody.
Yeah.
Oh, absolutely, man.
Gary, always good to have you, man.
Thank you, Neil. Always a pleasure, my friend.
All right, chuck it, baby.
You know it.
Neil deGrasse Tyson here, closing out yet another edition of StarTalk Special Edition. This one on hibernating in space. As always, I bid you to keep looking up.